Yes, thank you for the introduction, and I want to say thanks for the invitation to come and speak here. So my talk will be about applications that use algebraic geometry and tensors in them. So there will be tensors in this talk, maybe not as many as in the other talks, but this is an application on quantum chemistry, and I start with a picture here of a very wrong picture of an atom. I know that, but I still think this picture describes the objects that we will be working with. So we have an electron, it has a nucleus, we have orbitals, and we have electrons. Now, I can go from here. So where do we start? We start with the Schrödinger equation. So we fix integers, d and n, and d is going to be the number of electrons in an electronic system, and n is going to be the number of orbitals in our system. Now, we're going to work over a discretized Hilbert space. Now, the space of orbitals is an infinite dimensional space. It's a space of smooth functions from r to the 3 times the spin part. But in algebra, we don't want to work in an infinite dimensional space. So what we do is we discretize this space, and we end up with a vector space that's isomorphic to the exterior power of r to the n. And as a vector space, we have basis vectors, which I will shorthand write as e to the I, where I is a subset of n, numbers 1 to n of size d. Now, the objective is to solve an eigenvalue problem for a symmetric matrix called the Hamiltonian. Now, this is an eigenvalue problem. We learned that in linear algebra. Some people, maybe even in this room, we know how to solve this, right? Now, what's the problem? What's the size of this matrix H? If you know, you can say. Sorry? Yeah, it's a n choose d, so yes, n choose d. So it's an exponential size. So for n equal to 100 and d equal to 50, this number, we're not even going to be able to look at this matrix. It's a big problem, right? Now, what do? We approximate a large linear algebra problem with, I say here, a small nonlinear algebra problem, but what does small mean? With a smaller. It's not as big. Now, okay, now I'm going to unapologetically advertise a field and a book by my advisor and Matthias, who's here. So what is nonlinear algebra? So nonlinear algebra takes problems or tackles nonlinear problems using tools from many fields. So mainly from algebraic geometry, combinatorics. With algebraic geometry comes commutative algebra. And also we utilize tensors in multilinear algebra. And then also we can utilize convex and discrete geometry and algebraic topology. In this work, we mainly utilize the first 4 fields to solve our problem. And what we do is we focus on computations and applications, along with some theoretical underpinnings. All right, so we're going to start with some tensors. So instead of working in the deep exterior power, which is a vector space, we're going to work in the whole exterior algebra called the Fock space. Now, since we're working in an algebra, we can define exterior and interior products for each basis vectors. And we do this by introducing a creation operator that uses wedges a basis vector to your element, psi. And then we have a dual annihilation operator that hooks an element, a basis vector EP from your psi. Now, what does hook mean? Here, hook means the dual operation of the wedge product. So you can think of this as if you were working in the dual space of like particle hole symmetry. So instead of EI, we were working with E of everything but EI. And we would wedge EP, and then we would dual it again. So we're moving. It's the dual operation of removing an element from the wedge product, but with an appropriate sign. Now, these operations are endomorphisms of the Fock space, and they are called the creation and annihilation operators. Since if you think of a basis vector EP corresponding to an electron on orbital p, what these operations are doing is that they're creating and annihilating electrons on orbitals. All right. Now, these operators, they fulfill anti-commutator relations. So first, most of them anti-commute, except for the creation operator P does not anti-commute with the annihilation operator AP. We get here a 1. Now, what does that mean? Now I'm just restating what I said before. This is not really a proposition. So the creation and annihilation operators span an algebra called the Fermi-Dirac algebra. This algebra is also known as the Fermi-oscillator algebra, Carr algebra, and so on. And this is a special Clifford algebra associated with this quadratic form. All right. So this is this following quadratic form. And this is a restatement of what's happening here. All right, so what's so important about this? So the most important part here is Wick's theorem. So first I will state Wick's theorem here in the way that I would state it as an algebraic geometer, and then the form that's maybe more known in the quantum community. So the theorem is that the relations above, so the relations here, these anti-commutator relations, they generate a two-sided ideal that define our Fermi-Dirac algebra. And these relations, they form a Grobner basis with respect to a degree lexicographic order. And the important part here is that our standard monomials for this Grobner basis are these here. So what does this mean? So this means that the Fermi-Dirac algebra is isomorphic to a vector space generated by these standard monomials. So these standard monomials are the basis vectors of our vector space. And as a vector space, the dimension is 2 to the 2n. So maybe we can also notice that the Fermi-Dirac algebra contains all endomorphisms. Because the space of endomorphisms for the Fock space is also of this dimension as a vector space. Now, a restatement of Wick's theorem, it says that any element in the Fermi-Dirac algebra can be written in terms of the standard monomials. And this is called standard representation, often called normal ordering as well. The important part is we can write them with all the annihilation operators on the right, on the left, and all the creation operators on the left. Right, sorry. All right, there. Questions so far? Yes, so in the Fock space, so yes, in the most cases the indexes should be both, you mean here IM and BM here, right? Or is that what you mean? Yes, yeah, so if we're working just in the Fock space, this can be any size for L and M. Don't have to be the same number, but in the end we will have them as the same number, yeah. So if we fix this L and M to be the same. Oh, okay, I see. Okay, yeah. No, but in the case where they're equal, we get endomorphisms of exterior powers, because, yeah, I'll show that later, which is what we want. Now, all right, so, okay, why is Wick's theorem so important? Now, as I said before, these elements in the Fermi-Dirac algebra, they're endomorphisms of the Fock space. So that means they have a 2 to the n by 2 to the n matrix representation. Now, one way to get this matrix representation is to get the matrix representation for the creation and annihilation operator, and then treat this as a matrix algebra with a matrix multiplication. Now, that requires many matrix multiplications. Another way to get the matrix representation is to apply basis vectors on the right side and the dual basis vector on the left side. And another important point here is that the basis vectors can be written as creation operators acting on the vacuum state. So the vacuum state is the unit vector, or the unit 1. There's no basis vectors in this wedge product, the empty wedge product. Now, all right, so now the entries of the matrix become this long operation or long element in the Fermi-Dirac algebra acting on the vacuum state on here, and on the left, the dual vacuum state. Now, if we write this long operator in terms of the standard monomials, we see that we are applying annihilation operators on vacuum states, meaning you can't delete something where there is nothing there. And on the other hand, we're creating the dual of the vacuum state is the whole wedge product of all the elements. And we are trying to create something. We're trying to create an electron where there already are all of the electrons. So that's also 0. So all of the parts become 0 except for the constant term of the standard representation. And important here is an example that shows how to calculate these terms, or these entries of the matrix. Is here I take an example of, we have the word here in the Fermi-Dirac algebra, and we're looking at the UVRS element in the matrix representation. And what we do is that we take all complete matchings, where we match an annihilation operator with a creation operator to its left. And there are 4 such matchings, and these all correspond to products of delta functions. And so this entry in the matrix is this following delta function that is going to be a sum of 1, negative 1s, and 0s. All right. So the good thing about this is that we can get the matrix representation. The complexity of solving this is it's just constant, or depends on the size of the length of the word. And then we need to do this for n to the n, or to the every element in the matrix. So it's not so hard to compute the size of the matrix if the matrix is not too big. Yes? Yes, exactly. Exactly. So yeah, I'm explaining how to get the entries of, so I have an endomorphism in my algebra, and I want to get the matrix representation of that. And this shows me how to get the entries of each matrix element in a nice way. Yeah. And usually you don't even want to calculate the full matrix, and then this is a very fast way of getting submatrices of these endomorphisms. All right, so now I've talked a bit about the Fermi-Dirac algebra. So why do we need it? What we're going to do is that we're going to look at the specific operator in this Fermi-Dirac algebra called the cluster operator. Now, the cluster operator is defined as this following sum here. So what we're doing is that we're taking a combination of all the standard monomials where we annihilate from the first d orbitals. So here I mark these are called the occupied orbitals. So if you have the first d, or if you put electron on all the first d orbitals, this is called the reference state. And this is the state we're going to start with. So what we do is we allow to delete from any of the occupied states, and then we want to create electrons on the virtual states, not the first d. And these are then called excitation operators, because they are exciting electrons from the occupied states to the virtual states. So an example here is that this excitation operator deletes the first orbital and the third, adds them at the fourth and the fifth. We just take all general linear combinations of this. Now, and the important part here is that here should be an m. So it was a good question, because here we want the size of B and I to be equal, because we are not looking at ionization or electron attachment. We just want to excite electrons in our system. So we want to have a fixed number of electrons. So this endomorphism is actually an endomorphism on the exterior power instead of the whole Fock space. So we can move back down to the exterior power, which is smaller. All right, so what do we do with this matrix? Now we define a parameterization. So we have here two vector space, and important part here, I move on to the complex numbers. Later on, I will move on to the projective space. This is just because it's nicer to work in complex space than real space, and later on it will become nicer to work in projective space. Now, the vectors in my vector space H are called quantum states. This is a name known in quantum information. Now, I couldn't find a good name for the coordinates, so I gave myself the liberty to name them myself, and I called the coordinates the Plücker coordinates. And the reason for that becomes clear later, but we see that these coordinates are indexed by sets of size d, so these correspond to Plücker coordinates in the sense they are defined for Grassmannians. But it becomes clear later why I call these Plücker coordinates. And then I take another copy of this exterior algebra, and I have vectors x, who are called cluster amplitudes. Now, I define an exponential parameterization, and this is a nonlinear bijection between these exterior powers, where the quantum states are parameterized as the exponential of the matrix corresponding to the cluster operator, and then I just take the first column of that matrix. So the cluster matrix, we can create it like we did with the Fermi-Dirac algebra using Wick's theorem. Now, this is a matrix of size n choose d times n choose d, because I said this is an endomorphism of just this exterior power. And what turns out, it's a strictly lower triangular matrix. That's very important because as an algebraic geometer, I don't really like working with exponentials. Now, that's not an algebraic function. However, since my matrix is strictly lower triangular, it's nilpotent. It's nilpotent of order d, which means that the exponential of a nilpotent matrix, the entries are going to be polynomials of degree d, or less than or equal to d. So that's why this becomes interesting to us. So this parameterization is used in coupled cluster theory. We'll see later on how it's used to approximate the Schrödinger equation, but we're going to start by looking a bit just at this exponential parameterization and its algebraic properties. All right. Is everything clear from here? All right. Now, an example of a cluster matrix to visualize this is that here, if d is equal to 2 and n is equal to 5, we have this following matrix here. See, it's strictly lower triangular, and we take its exponential, and what we care about here is the first column of this exponential. And this is the parameterization of the quantum state. It's a bijection, so the image is going to be the whole exterior power. But we'll see later on some interesting stuff. All right. Now, finally, we get to varieties. So I'm going to take a subset of numbers 1 to d, and I'm going to call this the truncation set. And for people that are familiar with coupled cluster theory, choosing a singleton 1 will correspond to coupled cluster singles, singleton 2 will correspond to coupled cluster doubles, and then 1, 2 is CCSD, 1, 2, 3, CCSD, T. So these are known approximation methods of the Schrödinger equation. And so what we do is that I'm going to first define a projection for the set sigma that projects elements in the exterior power onto coordinates whose excitation level, so the number of electrons in the basis, so a basis vector that says a number of electrons in our orbitals is the number of electrons on a virtual orbital is going to lie in sigma. So this is written out here. And now we're going to, so just the basis vector, for example, E245 is going to have 2 electrons on the virtual orbital. So its excitation level is 2. So it's only going to be 0 unless we have a projection onto sigma with a 2. Now, we restrict our exponential map to this subspace, the projected subspace of V, of the exterior power. We project onto these vectors with the correct excitation level. And now, the Sverrisdottir closure of the image is called the truncation variety. Now, I no longer have a bijection. I only have an injection, so the image is something interesting. And we're going to call the Sverrisdottir closure of this the truncation variety. All right, now like Alexander asked yesterday, a variety comes in, what do you ask it? I might first ask, what's your name? Because I might already know you. If I don't, I will maybe want to ask, what's your dimension? What's your degree? Are you reducible? What are your defining equations? These are the questions that I'm interested in. Now, I can answer 2 of these questions right away. All of these varieties are irreducible, since they are image of an injective map from an irreducible subspace. Subspaces are irreducible. The image of an irreducible, yes. 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 It's going to be the number of basis vector with excitation level in sigma. And this is actually, yes, the other point is that we know the dimension. The dimension of this subspace is here K, that we're projecting onto. And this is all excitation. This is the number of basis vectors with excitation level in sigma. So here I say I can remove any for I in sigma. I can remove from the occupied orbitals and add to the virtual orbitals. So this K is a number we know, and that's the dimension of our truncation variety. So another answer we know is we know its dimension. All right? A third thing we know is that we do know its defining equations. So this exponential map is actually really nice. It's a nonlinear bijection. It has a polynomial inverse. So everything is nice about this parametrization, I would say. So we have a polynomial inverse, which I will write the inverse maps as xi of psi instead of psi of xi, psi I of x, and they are found using Möbius inversion. So we have a formula for finding these inverse functions. We actually have an explicit formula describing these inverse functions, and there we use Möbius inversion and combinatorics to get that. And these polynomials are going to be our defining polynomials for the truncation variety. So first, in the affine case, we have a very nice theorem here that the prime ideal of the truncation variety is a complete intersection, and it is the ideal generated by inverse polynomials that are indexed by sets that don't have excitation level in sigma. So we take not the ones that we want to project onto the excitation levels that lie in sigma, but the ones that don't. Now, if we projectivize this, we just get, by definition, the homogeneous prime ideal for the truncation variety. This no longer has to be a complete intersection, and we do that by homogenizing the inverse polynomials, and then in the end we saturate by the homogenizing variable. Now, that might be harder to know the defining equation of the homogenized ideal, but for the affine case, we know. Now, let's look at a few examples of truncation varieties. I've defined these abstract varieties. Now, what do they look like? So I take an example here. We have 3 electrons in 6 orbitals, and then we get 6 distinct truncation varieties. They all live in the projective space P19. And the first 3 cases are very simple. These are linear spaces. So for sigma 2, sigma 3, and sigma 2, 3, we get a linear space. So here, this is the one that's maybe interesting to chemists, but the other 2 are interesting as a mathematical excursion. Now, if we pick sigma to be 1, 2, we get a hypersurface defined by what we call the master polynomial, which is this inverse polynomial of the bijection. Now, for 1, 3, we get a variety I don't know. So I just say everything I know about it. I know I have a variety. It has dimension 10. I can calculate its degree in Macaulay. I get that its degree 41, and its ideal is generated by 25 quadrics. So its homogeneous ideal is generated by 25 quadrics. Now finally, if sigma is 1, I get the Grassmannian. It's of dimension 9, degree 42, and it's generated by 35 quadrics. Now, this is the reason why I chose to call the coordinates of the quantum states Plucker coordinates. So do we get the Grassmannian in other cases? Well, we'll see. So first, we see that when do we get a linear space? We saw that in 3 of the cases we looked at, we get a linear space. So in many cases, we seem to be getting linear subspaces. These are very simple to work with, very nice varieties. Now, the truncation variety is going to be a linear subspace if and only if we have this condition on sigma. This is a nice condition that enables us to classify all the time where a truncation variety is linear. So we say that if you have I and j in sigma, and their sum is less than d, then their sum should be in sigma. So in a sense, we're saying it's closed under addition. And a case where this happens is that if you have two electrons in any number of orbits, then this truncation variety corresponding to CCD is just this linear space here. Now, another interesting case is that we get the truncation variety V1 is the Grassmannian Dn in its Plucker embedding. We really like the Grassmannian, so I'm going to say that the truncation varieties are a generalization of the Grassmannian. Now, I also say here that this is a restatement of a theorem that's already been known for a long time, and it's called Thouless theorem. The Thouless theorem tells you that, in very different words, that coupled cluster singles corresponds to finding separable states, non-entangled states. So how does that translate to saying that our truncation variety is in the Grassmannian? Now, the Grassmannian actually is the variety of all separable states. So first I define the Grassmannian is a set of d-dimensional subspaces in an n-dimensional space, vector space. Now, I can always say that a subspace of dimension d is the row span of some matrix, of some full rank matrix of size d times n. So here I have a matrix M, and let's say the row span of this matrix is V. Now I can perform Gaussian operations on this matrix. It's not going to change the row span. So both of these matrices have the row span V. But what's important here is that up to a scalar, the d by d minors of M do not depend on the choice of basis. So Gaussian operations are also just a change of basis. So I can define the Grassmannian as the image of the map of d by d minors, and I rewrite d by d minors as a single wedge product of the rows of M. So the wedge product of the rows of M are the d by d minors of M, and these are, in fact, the separable states. So they're all separable states. So the Grassmannian is the variety that contains all separable states. So this theorem basically tells us that the first truncation variety just gives us separable states. All right. So now I'm going to go into the point of all this. We're approximating the Schrodinger equation. We started with the Schrodinger equation. I said it's too big. I'm going to truncate it and create a smaller nonlinear problem. So what I do here is that I say the coupled cluster equations are, for a truncation set sigma, are defined as the truncated eigenvalue problem. So I require my quantum states to lie in the truncation variety. Now, I can't expect to solve the Schrodinger equation if I've already restricted my quantum state to lie in a variety. There's not going to be any solutions. So I need to loosen the conditions here as well. And what I do is that I project these equations onto the coordinates that correspond to excited states that lie in sigma. Now, this is a square system. Or it's not a square system. This is a system. The expected number of solutions for a generic matrix H here is finite, because the dimension of this variety is the same as the number of constraints composed here. So we expect there to be a finite number of solutions to these equations. Now, we define the CC degree of a truncation variety to be the cardinality of these number of solutions, or the number of solutions for a generic matrix H. This is a fixed number, and it tells us the complexity of solving these equations. Now quickly, we get upper bound for this number very quickly by using a version of Bayes-Two's theorem that says that the degree of an intersection of two varieties is less than or equal to the product of the degree of the two varieties. We are intersecting two varieties. We're intersecting the truncation variety and this cone of the Segre variety. Now here, the degree of this variety here is the dimension of that, or the number of equation there, and the degree of the truncation variety is there. So this is just a nice upper bound we get straight from these equations here. All right. So I'm going to just have a few tables now. We have a lot of theorems and definitions. So now there's a few numbers. Let's take a little break. So I have an example here that I have 3 electrons in 7 orbitals. And I get 6 truncation varieties, and I'm going to tell you everything I know about these. I have it there. Dimension of the truncation varieties, the degree of the truncation varieties, the number of, or the Betti numbers of the generators. So I have here no generators of degree 1, and I have 140 generators of degree 2. Here I have 16 linear generators, 30 linear generators. Here I only have 7 generators of cubic generators, and so on. And then I write out the CC degree, the number of solutions to the CC equations for a generic matrix. And I write down the bound that we had on the previous slide. And we can see the bound is tight here. In the linear cases, the bound is exact. Here it seems to be kind of double. Here, not so far from it, and so on. And then another example is for D4, D equals 4, N equals 8. And this kind of shows the boundary of how large computations we can do, is that this turns out to be a very large computation. We have here 69 variables. It's a big polynomial system to solve, even in like a Julia or anything. But we have a few linear varieties, which I won't show, and then we have nonlinear varieties here. And we can see the CC degrees. The Grassmannian is 150,000. Here for single doubles, it's about 17 million solutions that we would expect, and so on. And we can also see how the bounds are doing compared to the exact CC degree. All right, so in a few cases, we actually have an explicit formula for the CC degrees. So these are 2 cases where we have an explicit formula. So in the linear case, we might have noticed that the CC degree just seems to be the number of solutions to a smaller eigenvalue problem. So we say that if the truncation variety is a linear space, then the CC degree is the dimension of that variety plus 1. Now, the reason we do plus 1 is just because it's a projective space. We need to add 1. But in reality, the CC equations, they are just an eigenvalue problem for a symmetric submatrix of the Hamiltonian, and all complex solutions are going to be real. So in the linear case, these equations are much simpler. Now, another case we are able to solve, or get an explicit formula for the CC degree, is for the Grassmannian of lines. So then the CC degree of the Grassmannian of lines is 2 times the Catalan number of the n-1 Catalan number minus 1. Yeah, so this is actually we have a paper on why this is the number, and it's very interesting. We end up counting maximal chains in a poset that we create. And this number of maximal chains is this. So I'll go maybe a bit into how we are able to frame the CC degree in a nice way so we're able to make theorems like these. So what it turns out is that the CC degree, in most cases, is the total degree of a graph. So Mateusz talked about the graph of a variety, and it's by degrees. So I have a definition here, is that if I have a parameterization of a variety, its graph is the Zariski closure of the set of the graph. Now, this is a variety of the same dimension of our original variety, and its total degree is defined as the sum of its by degrees. Now, there's another definition of the total degree that says, let's take the affine cone of this variety and then projectivize again, and then we no longer work in product space of projective spaces, but I like defining it as the sum of its by degrees, because as we saw, there are many interesting properties about these by degrees of graphs, like they form a log concave sequence, and so on. So this theorem tells us that in many cases, we can calculate the CC degree by just summing up the by degrees of its graph. And there are people that are interested in looking at graphs of varieties and what are its degrees. I'm one of them. And yes, and the most important part is that this result extends to any parameterization of a truncation variety where we have this nice condition. And such parameterizations exist in all cases of interest. I say all cases of interest is these aqueous-based set excitation truncation sets. So for 1, 2, 1, 2, 3, 1, 2, and so on. It's these sets here. We can always find the parameterization of the variety, and then we can find the CC degree by understanding the graph of that variety. And this is what we did to prove the CC degree of the Grassmannian, and we are can also do this for the Grassmannian in general, but we don't get as a nice of a explicit formula. So for the Grassmannian, not just the Grassmannian of lines, we can describe this, but we don't get a nice explicit formula for the CC degree, but we use the same method. All right, yeah, so now I promise to have a few graphs and numerical excursions in the end. So now here, this slide here, I'm comparing our bound with previous bound. So this question of what is the number of solutions to the coupled cluster equations has been asked before. We were not the first to ask it. And this slide is not meant as a criticism of how to compute bounds, but more as the purpose of this is to show the importance of understanding the structure of your algebraic equations to get closer bounds. So here, we investigate the scaling of the CC degree for d equals to 2 when n scales for CCS and CCD. And here we have a previous bound that was found using Bézout's theorem. So if you have a set of polynomials and you want to know, you know nothing about the structure of these polynomials, you can always find an upper bound of the number of solutions to that by multiplying the degree of each polynomial. It's going to give you an upper bound to the number of solutions to that polynomial system, or if it's zero-dimensional. Now, well, if we would do this for example, the eigenvalue problem, what would our upper bound be? The eigenvalue problem can be written as a system of degree 2 polynomials. So n distinct degree 2 polynomials, our upper bound would be 2 to the n. But we all know that the number of solutions to the eigenvalue problem is going to be n. So it's very important to know sometimes the structure of your equations. So here we have the new bound that we got here. And we compare it with the exact CC degree. This black line here says we have a conjecture, but this is actually proven now. So this is the black line here is the exact CC degree. This is the bound before, and this is either the Bézout bound or the mixed value bound. And then here for CCD, our bound is exact, and previous bounds are, different. And then also here we have the CC degree of 3 electrons and 6 spin orbitals. The mixed value bound is 2 to the 27th, and you're not going to solve anything with this many number of solutions, but it turns out the number of solutions is 55. All right. So before, I have plenty of time. So before I show the last numerical example, I'm going to explain, yes?
In the previous slide, so the CC degree is computed in which...
This one. So here, this is actually another theorem we have that I didn't show on these slides that can prove this CC degree. But you can compute it we computed it in Julia homotopy with monodromy, yes.
Can you repeat what CCSD coupled cluster?
Yes. So I'm going to repeat what CCSD coupled cluster means. So we defined the coupled cluster equations here. So we defined the coupled cluster equations for a subset sigma of numbers 1 to d as the following here. But in chemistry, these are, so for the set sigma 1, 2, this is called coupled cluster SD. So it's the coupled cluster equations corresponding to truncation set 1, 2. So we have a different numbering here. So so these, so maybe I'll show here. So what we are actually doing when we're solving the coupled cluster equations, we are not solving them like how I wrote them down before. We are solving them as a square system. So the parametrization of our variety is here. And then we want to find an eigenvalue of this. But we just truncate here to sigma. So here, for the coupled cluster C SD, we have sigma 1, 2 here. Now, so I'm going to explain a bit how we solve our polynomial systems. So what we do is we use homotopy continuation. And there what we do is that we define the family of coupled cluster equations. So this is a set of polynomial systems for different matrices. So for any matrix G, here we get a different set of coupled cluster equations for that matrix. And the variables of the systems are the eigenvalue and the variables, the cluster amplitudes. And they live in C and this subspace, V sigma. And the parameters of this family are the elements of this n choose d times n choose d matrix, G. Now we want to find the roots of a polynomial system in this family corresponding to a specific Hamiltonian of interest, not necessarily a generic matrix. We want to know what are the number of solutions for a Hamiltonian corresponding to, for example, lithium hydride. So what we do first is that we use monodromy methods, which I will explain on the next slide what are, to solve a generic system in this family. And this will also give us the degree, the coupled cluster degree, because we define the coupled cluster degree to be the number of solutions for a generic matrix. And then we use parameter homotopy to track these generic roots to the roots corresponding to our Hamiltonian of interest. And here's a paper where we go deeper into this. So here, what is monodromy and what is parameter homotopy? So a homotopy in the coupled cluster family with start parameter G and target parameter G prime. Here we define it as this map here that takes a parameter T in the parameter space. Okay. So we have here, so we have this T, which is just a complex number. And for each T, we're going to get a different matrix in the parameter space. So our parameter space are matrices, n choose d times n choose d. Matrices. A drink. And at each point T, we get a different system in the coupled cluster family. But we require the start system to be this CC equations for D, G, and the target system is these CC equations for G prime. And what we do is that we solve the initial value problem for the Davydenko differential equation. It's written out here, but we require the start solution of the solution path x to be a root of this system here. So we need to know one root of the system. And now this endpoint of our solution path is a root of our system G. Now, for a solution of the Davydenko differential equations, the other endpoint is going to be a root of the target system. So by solving this system, we are, for example, if G and G prime are different, we have here all the roots of G. Let's say we know them all. And we track them with the Davydenko differential equation to roots of G prime. Now what can happen is three things. You can have what happens here in the dashed dotted line, very nice. You start with a root of G, and you end with a root of G prime. Now on the solid line here, we get a root that goes off to infinity. Not all roots of G are going to end up being a root of G prime. And the third thing that can happen is that we can track to a singular solution. So what we want is that we want our start system G to be generic in the sense that it has the most number of solutions and no singular solutions. Our target system, however, does not have to be generic. So this is what parameter homotopy does. It takes a generic system, which we know the roots of, and it tracks these roots to the roots of the systems we don't understand. Now, what monodromy does is that if we have a generic system and we don't know its roots, we only need to know one root of that system to find all the roots of that system. So what we do is we do the same thing. We start with one root we know, but now our target system is going to be G again. It's going to be the same as the start system. And then this parameter loop here, T, is going to be, I said it. The parameter path here for T, gamma T, is going to be a loop. And what we do here is a picture of a very simple system with three roots, 1, 2, and 3. And we do monodromy on this system. Say we know the root 2, and we track it, and we end up at a root 1. So we found one other root. Now we know 2. Now, okay, we try this again. We found 2 again. Okay, we didn't find anything new. Okay, now we need to find then a new path loop there and try again until we hopefully find the last solution here. So what monodromy does, it generates new loops in the parameter space and tracks them to try to find new solutions. And it stops once it thinks it's found all solutions. And there are some criteria for that. But this is a numerical method. It's not guaranteed we find all solutions, but if we can verify those solutions, it gives us a lower bound. And there are also some tests that sometimes work to check that these are all solutions, some trace tests. So what monodromy does is that it solves a generic system where we only know one solution. That solution can be found with Newton's method. It's not hard to find one solution of a system. And then we take those solutions of this generic system and we track them to our difficult system that's not generic. All right, so what we're doing here is that we did this, exactly this, for the Hamiltonian for lithium hydride. So we have now a molecule, lithium hydride, and the lithium hydride has 4 electrons, and we choose a minimal basis set. So we assume that we have 8 orbitals. So for each orbital, in reality, we're saying we have 4 orbitals, but each of them has a spin up and a spin down. So this is the smallest possible number we could have picked, and equals 8. And we're picking sigma, our truncation set, to be 1, 1, and 2, and this corresponds in the literature to couple cluster single doubles. Now here, for comparison, the CC degree is about 17 million. I say not exact because we use monodromy, and for such big systems, we are not able to verify this. Now, but we track these 17 million solutions we found to the solutions of the Hamiltonian for lithium hydride, and we get 16,000 solutions. So many solutions are going off to infinity. These Hamiltonians have some structure that's very special compared to just a generic matrix. So that can be utilized maybe sometime, but not now. And of these 16,000 solutions, we have 2,000 solutions that are real valued eigenvalues, and 1,280 solutions that are actually just real solutions. Now, on these graphs here, we compare these 16,000 solutions, here marked in blue are the blue points, with the 70 eigenvalues of the Hamiltonian. Now, the Hamiltonian for lithium hydride is actually just a 70 by 70 matrix. So we can solve the full eigenvalue problem. And we compare here to the CC solutions are the blue dots, and the lines here are the actual eigenvalues. And on the second graph here, we compare these CC equations, and we leave the ones that are machine precision close to the actual eigenvalues. Yes? No, actually, yes. So the runtime is on a server, an MPI server, on 144 threads. Yes, so it's a very large computation. Yeah. So this runtime here, in the monodromy, it took about 30 days on the MPI server. We used 144 threads. The great thing about these methods that I'm showing you here, they're very parallelizable. Like, they're as parallelizable that they can be. So you can run everything in parallel, but still, these are large calculations to find all solutions. So this takes about 30 days, and the parameter homotopy is faster, and it takes about 13 days. Yes. Yeah. And yeah, so then we compare these solutions to the actual eigenvectors to see, eigenvalues to see which CC solutions are actually approximating eigenvalues, because that's what we wanted to in the beginning. We can see here, they're not approximating all of them, but what we most care about is that they approximate the ground state, but they also, in this case, also seem to be approximating excited states. Yeah, I think both out of time, or it's a good time to have questions, and I'm also done, so thank you.
Thank you.
Questions? The closest.
So, sorry, you said something about coupled cluster degree of the Grassmannians other than G2N, something that you can do them, but not with a formula?
So we don't have a formula for them yet. So what we do also for this Grassmannian here is that we find a toric degeneration of the Grassmannian that lifts to the graph. And this can be hard because our parameterization of the Grassmannian is a birational parameterization, and it has not been studied as much as other graphs of the Grassmannian. And so we found these toric degenerations, but we don't have an explicit formula for the degrees for Grassmannian, larger than just Grassmannian of lines.
So do you have it like as a volume of some explicit polytope?
Exactly, yes. We have the volume as some specific polytope. Yeah.
Thank you.
Yes.
Yeah, thank you for a very nice talk. I just got confused at the end with the numbers, and I wanted to ask a bit about this. Because like the initial premise was, if I recall correctly, that we had like this large Hamiltonian, like you take n and d, and maybe d should be like n/2 or something, like not a constant, and then we have like for large n we have an exponentially sized Hamiltonian, right? And we want to basically reduce this large linear algebra problem to a smaller nonlinear algebra problem. So, but here in the end you get like somehow 70 eigenvalues of the Hamiltonian. Is that of the exponentially sized thing is like 70 by 70?
Yes.
And
Exactly.
CC solutions are like 16,000?
Exactly, yes, exactly. So you're totally right. So actually this smaller nonlinear algebra problem is not easier to solve. But what the chemists do is that they don't fully solve this problem. They have a start solution which they think is a good approximate guess, and then they use Newton's method to find, to approximate that solution to a solution of the CC equations. And they, like, if they start close enough to the ground state, it should get that solution, because they only care about one solution. And then it is much faster than solving the full eigenvalue problem. What we are doing is that we want to understand the solution spectrum. So for example, here, if you start, so we wanted to see how does the solution spectrum look like? Because if you solution starts here, or okay, it's probably going to start on the real line here. Are you actually approximating the ground state? So I will not be selling this as a method to solve the Schrödinger equation to use monodromy and then get the solutions, because that's very complicated. This is more an algebraic exploration of this polynomial system and how the solutions look like. Yeah.
Okay, so what the chemists do, we should maybe like interpret it like basically similar to what machine learning people do, is like that they take like some complicated non-linear function and then they optimize it with local optimization.
Yes.
And then they hope that they chose it their model nice enough that the local optimization works.
That's exactly what it is. Yes, exactly. So then we have, like, for example, this algebraic statistics that take like the calculus ML degree, even though the machine learning or like statisticians don't really or the optimization degree. They don't fully solve the optimization problem. They use local methods to get to local minima or local solutions. But this is to show how big is the system, how many solutions are there to the system actually. Yeah.
Okay, thank you a lot.
Thanks. Last one for the sake of time.
Yeah, thanks, Svala. Fortunately, I've seen this before, so I knew a bit more. But I have one question that was just sparked, because you said that you can also give this method, essentially the monodromy solver, you can give the exact like ground set, for example. Mm-hmm. How would then like the times scale? Do you know? Would it be just like much faster?
If you would know the ground state,
yeah,
then you would want to. Then it would just depend on how many you would want to find. So you could stop at some point. So what you could do if you have the ground state and wanted to try to find excited states is that each tracking is not going to take. It's just similar to the Newton's method, because what you're doing is you're utilizing you use Newton's method to track solutions. Mm-hmm. So that would be much faster.
So also the CC degree is reduced?
Oh, no. The CC degree is always going to be hard to find, because the problem is that you're tracking 70 million solutions.
Yeah, okay,
and that's going to take a. But if you wanted to find a few more solutions from one solution, finding one solution does not take a long time. But the length of this is that you need to do this so many times to get up to 17 million.
Okay, yeah. I think I had a second question, but I think for the sake of time, I'll ask you later.
Okay.
Thanks again.
Thank you.